Okay, so this is lecture number 1, part 2, continuation from the previous lecture. Lecture number 1, part 2. So we're going to continue our discussion on the graphing of functions. So today we're going to work on graphing rational functions. Y is equal to f of x, which is equal to p of x divided by q of x, where q of x, of course, is not 0. Now, in this discussion, we're going to assume that p of x and q of x are polynomials. We're going to postpone dealing with other types of functions for p and q until subsequent lectures. So I'm going to start off by giving you a set of rules for how to graph rational functions. And the first rule is extract vertical asymptotes. Right? And the procedure goes as follows. So first, factor p of x and q of x. Now in this class, I assume that you have sufficient competency in factoring polynomials, yes, polynomials. And if you're a little bit weak in this area, there's a lot of literature on my class websites in my algebra and trigonometry sections which describe how to factor polynomials, and there's of course a lot of information on the web where you can get those details. And you probably have access to tutors somewhere around the UAA system. So if you're a little bit weak in factoring, please come up to speed quickly in this area. I'm not going to spend very much class time on going over the rudimentary aspects of factoring. So anyhow, back on task, we're going to factor p of x and q of x and remove common factors. Right, so if you have a factor that's common in the numerator and a factor and in the denominator, go ahead and cancel those factors out. Right, so i.e., that is, cancel the common factors appearing in the numerator and denominator, and work with only what's left. Right. So once you do this, set the denominator equal to 0 and solve. If A is a real solution, okay, not complex, we're not dealing with complex numbers in this class. So if A is a real solution, then x equals A is a vertical asymptote. Okay, so that's the first thing we want to hunt for when we're graphing rational functions. Second thing we want to look for are horizontal asymptotes. So we want to extract horizontal asymptotes. So the first thing we do is, well, before we proceed, I want to give you a definition. The degree of a polynomial is the largest exponent in the polynomial. Okay, so with that in mind, to investigate the presence of horizontal asymptotes in your rational function, the first thing we do is this. If the degree of the numerator, p of x, is less than the degree of the denominator, q of x, then the line y equals 0, or the the line y equals 0, or the x-axis in other words, is a horizontal asymptote. And I'll write horizontal asymptote as HA. Right? If the degree of P of x is equal to the degree of Q of x, then the line y equals P over Q is an HA. And so let me tell you what P over Q is, okay? Where P is the leading coefficient of the polynomial in the numerator, and Q is the leading coefficient of the polynomial in the denominator. Now, I assume you have some knowledge of what leading coefficients are, but just to remind you, let me go ahead and construct one and show you how to identify the leading coefficient. So if we have y is equal to f of x, say negative 2 x squared see, where are the rules here? Negative 2 x squared, say, minus 5x plus 3. So consider this polynomial. In this case, the leading coefficient would be what? See if I can copy it here. Bear with me. All right. So consider this polynomial. The leading coefficient is the coefficient on the term of the highest exponent. So in this case, the leading coefficient would be negative 2. Okay? So right there. So y equals P over Q is the horizontal asymptote. All right, and then there's another consideration. Let's see if I can move this elsewhere. So I'll move that off to the side. So the other consideration for obtaining asymptotes Part C, if the degree of P of x is greater than the degree of Q of x, that's the third case, right? Then there is no horizontal asymptote. All right, so we'll follow this procedure for now for identifying horizontal asymptotes of a rational function comprised of polynomials only. Later on, we're going to formalize these definitions, in particular in Chapter 2, using infinite limits. Okay. The next thing we want to look for are the slant asymptotes of the rational function. And I'm going to give you a rather limited procedure now, and later on we may investigate other techniques for finding slant asymptotes. But to extract slant asymptotes, it goes as follows. If the degree of P of x is equal to the degree of Q of x plus 1, then the slant asymptote is P of x divided by Q of x minus with not minus, excuse me, with the remainder discarded. Okay, and I'll give you an example of how to compute that in just a second. All right. The fourth thing we want to consider when sketching the graphs of rational function are extract the holes. Extract the holes of the rational function. So, for instance, the way we do this is factor P of x and Q of x and check for common factors. Holes occur where those common factors equal 0. And I'll show you how to compute the coordinates of the holes forthcoming with the example that I'm going to do right now. So let's do an example. Yes. So let me write the function. We'll do an example of so let's say y is equal to f of x, and which is equal to, and how about let's go x cubed minus 8 divided by x squared minus 4. So and I'll write that here. So, example. Sorry, I'm writing the equation on another monitor, and then I'll paste it in here. So, it'll let me copy, paste. Okay, so here we go. So So we want to sketch the graph of this rational function. All right, so the first thing we want to do is we want to factor the numerator and the denominator. So in doing so, I'll go to the next page. We note that what? P of x is the difference of two cubes, right? So P of x is x cubed minus 8. And so the difference of two cubes, as a mode of review, would be, for this polynomial, would be x minus 2 times x squared plus 2x plus 4. Right? And then the factorization of Q of x which is equal to x squared minus 4, which is equal to a difference of two squares. So that would be x plus 2 times x minus 2. Okay, so we've got two common factors right here, x minus 2. So the takeaway is that a hole is at x equals 2. So now we need to find the coordinates. We need to find the coordinates of the whole. So here's how we find the coordinates. F of x is equal to P of x divided by Q of x. And I'm going to go ahead and do the cancellation. And so after all the common factor cancellation, we'll have x squared plus 2x plus 4 divided by x plus 2. So the coordinates of the whole then would be x equals 2, and then we take the 2 and we plug it into what's left after the cancellation. So we plug it into this piece right here. And so when we plug it in, we'll have what? 4 plus 4, which is 8. 8 plus 4, which is 12. 12 divided by 4, which is what? 3. Okay, so the coordinates of the whole will be 2, 3, like that. All right. So there's our whole. Now, with this polynomial, we note that, looking at the polynomial structure again, we see that the degree of the numerator is 3, and the degree of the denominator is 2. So that means if we look at the rules, we have a slant asymptote. So we need to construct the slant asymptote. So let me show you how that's done. Now to construct the slant asymptote, what I'm going to do is I'm going to do polynomial division using long division. Now your choice of dividing polynomials, you may choose to use synthetic division, which is fine if you're more familiar with that. I know quite a few students in the past haven't really understood how to divide polynomials using long division. So I'll give you an example here. Dividing polynomials by long division is the same as dividing numbers by long division. You have to go all the way back to when you were, I don't know, what, third, fourth grade, fifth grade, when you were doing division of numbers. And so it's basically the same technique. Also, if you go to the class website at rfrith.uaa.alaska.edu/calculus/m200.php, you'll note that I've got some calculators posted on that page, and one of the calculators happens to be a polynomial division calculator. So if you're really struggling with polynomial division, you can try using that calculator. But you need to understand how to do so for things like homework and potential test questions. So anyway, enough said. I'll go ahead and do the long division as a mode of review. So we're going to divide the denominator into the numerator. Okay, and so I'll just go ahead and use the function that's left after the cancellation. It doesn't really make that much of difference. So we're going to divide x plus 2 into x squared plus 2x plus 4, okay, using long division. So the procedure goes, as with numbers, you look at the first two terms right here of the divisor, or I guess this is called the dividend. And so you ask yourself, how many times will x plus 2 go into x squared plus 2x? So you have to multiply x plus 2 by a factor to get as close as you can to x squared plus 2x. So what if we multiplied x plus 2 by x? Right, and in doing so, we have x squared plus 2x. All right. Let me erase this. So x times x plus 2 is equal to x squared plus 2x, just like you're doing long division with numbers. And then we do the subtraction, and so we're left with 0. And we bring down the remainder, 0 plus 4. which is the remainder. Okay, so what this means is we can't do the division anymore. So we discard the remainder, and retain the quotient, which is x. So the takeaway is y equals x is a slant asymptote. Okay. All right. So there's one detail. All right. So now this is the new stuff. Does this rational function have any horizontal asymptotes? No, it does not, because the degree of the numerator is one more than the degree of the denominator. So f of x does not have any horizontal asymptotes. All right. So how do we proceed with sketching the graph of this rational function? Well, we're going to use the techniques from Lecture 1, Part 1. We're going to use all of those rules that we discussed in the previous lecture with respect to graphing polynomials. Those rules come into play here as well. And we're going to use those rules combined with these rules that we've talked about today, aggregate them together to get a comprehensive drawing of the graph. So, next page. So the next thing we want to check for is symmetry. So let's say, oops, let me go back to black. Okay. Check symmetry. All right. So even check first, right? So we need to check f of minus x. So what is f of minus x for this polynomial? Excuse me, this rational function. Well, it would be minus x quantity cubed minus 8 divided by minus x quantity squared minus 4, and that is equal to minus x cubed minus 8 divided by x squared minus 4. And that does not equal to the original rational function, which was x cubed minus 8 divided by x squared minus 4. Okay, and that does not equal to minus f of x. And minus f of x, of course, is equal to minus x cubed plus 8 divided by x squared minus 4. Okay, so this graph has no symmetry. So f of x has no symmetry. So no help there. All right. What else do we check for? We found a slant asymptote. Okay, vertical asymptotes. So check for vertical asymptotes. All right, so let me copy the function again for reference. So here's our rational function, and now the hunt for vertical asymptotes would occur by setting this equal to 0 after the cancellation, right? So after cancellation, we're left with, I had that on the previous slide, right? So let me see if I can get that. That was x squared plus 2x plus 4. X squared plus 2x plus 4 divided by x plus 2. So after the cancellation of common factors, we see that x equals minus 2 is a vertical asymptote. All right, so we have one slant asymptote and one vertical asymptote and no horizontal asymptotes. Okay, so the next thing we want to deal with is we want to find the intercepts. So let's find the x-intercepts. X-intercepts, okay? And those are found by setting the numerator equal to 0 after cancellation. So after cancellation, notice that we found the holes first, and after we find the holes, then we'll hunt for the intercepts. Okay, so there's a kind of a precedence here, and for this particular function at least. So f of x is equal to x squared plus 2x plus 4 divided by x plus 2. All right, so the x-intercepts will occur by solving x squared plus 2x plus 4 equals to 0. Right? And so we can try factoring this quadratic, or we can try using the quadratic formula. So let's try and use the quadratic formula. So let me write it here for your reference. All right, so this is the quadratic formula for the technique for finding the two roots to a quadratic equation. And so if you recall, A is, for this quadratic, is equal to 1, B is equal to 2, and C is equal to 4. Now, when we plug in A, B, and C into the radical, we don't have to actually go through all of the details of solving this quadratic formula because, as I said, when we plug in A, B, and C into the radical, we'll have what? B squared, which is 4. This is the discriminant part, right? 4 minus 4, A is 1, and C is 4. Notice that we'll have a negative number under the radical, which means that this quadratic has complex roots. So if the quadratic has complex roots, then the indication is that there are no x-intercepts. So f of x has no x-intercepts. Okay? All right. And so far as y-intercepts go, we can explore or investigate if it has any y-intercepts. And that's found by setting x equal to 0 x equal to 0 in the rational function. And it looks like I may have a mistake here. I think it was x plus 2. So let me make that x plus 2. The fact that I had an error in the denominator didn't affect the computations for the x-intercepts because those are just found from the quadratic formula. So anyway, when x equals 0, f of x is equal to what? 2, right? So this means that our y-intercept is at the point 0, 2. Right, so we have computed the intercepts now. Right. The next thing we want to do is we want to check for the limit as x approaches plus or minus infinity. So next slide. All right, so let's see how I can do that. See if I have a symbol for that. Yeah, here we go. So what we're going to be doing is this. So this means, oops, that's not n, it should be x. Wrong formula, sorry. This symbology we'll see a lot in this class. Basically what it means is we take x and we make x very, very large. And so as you can see, as x grows very, very large, what would the output be for large values of x? Well, you see that as x goes large, this x cubed term dominates the x squared term, and they'll of course overpower the constants. So as x grows very, very large, the output goes to infinity, right? And so conversely, as x grows very, very small, which we represent by negative infinity, because negative infinity, for all intents and purposes, is a very small number with a large magnitude, that is. So we consider this. So x goes toward negative infinity. Well, negative infinity cubed is negative infinity. All right, so I'll have a negative infinity basically divided by, well, the negative infinity divided by, well, the negative x cubed, or x cubed term still prevails over the x squared term. And so what happens effectively is the numerator prevails over the denominator as x grows very, very small. And so the output then would be negative infinity. All right. So this is kind of a conceptual, abstract reasoning here. Let me draw this better. So that's negative infinity right there, negative infinity. All right, so that'll serve as guides for sketching the graph. All right, are there any other things that we need to talk about insofar as graphing the function? I can't think of anything else, so we are now in a position of sketching the graph. All right, so let me pull up the graphing calculator. I'll do that on the next page. So let me insert a browser, go to my online graphing calculator. Okay, so here we have our calculator. And what was the first thing we discovered was we had a vertical asymptote at x equals -2. All right, so that's shown by the red line right here. So here's our vertical asymptote. Then we had a slant asymptote, y equals up to x. Okay, and that will be shown by the blue line. So, right, and then we had a hole at, what were the coordinates of the hole? At 2, 0. So x equals 2. Y, let me see if so 2, 0. Okay. Was it 2, 0? Or was it, oh, I'm sorry, it was 2, 3. I beg your pardon. The hole we calculated was 2, 3. Yeah. So here is our hole. We had no x-intercepts, and we had a y-intercept at 0, 2. 0, 2. Okay. So there's our y-intercept and our hole. Okay. So now, oh, we did forget one thing, though. We forgot our table of signs. Yeah, so we can't proceed until we calculate our table of signs. So let's go back and calculate our table of signs. All right. I knew there was one thing I forgot, the table of signs. I was about to draw the picture, and I said, well, how am I going to know where to draw the picture, above the x-axis or below the x-axis? So let me insert a table. And let's see, we have 1, 2, 3, 4 factors, right? 4 factors. So let's just go ahead and make it a 5 by 5 table. All right. And so the factors for the numerator were what? X minus 2, and then x squared. Let's make these smaller fonts so I can get the content in the cells. So it was change font style to 12. Okay, so we had x minus 2. Then we had x squared plus 2x plus 4. That's the numerator. And then the denominator we had x plus 2, and we had x minus 2. And then we had f of x. All right, so let's fill in the table of signs. And then, so we draw our x-axis. So let's draw our x-axis. Like so. Okay. And this would be minus infinity here. This would be infinity here. And so we have the smallest 0 would be the 0 of this factor, which would be minus 2. So we'll plot minus 2 here. Now, yeah, minus 2. And then the next 0 occurred at x equals 2. Is that right? Yeah, so it appears to be right. And of course, x equals 2 and x equals minus 2, those happen to be not in the domain of the function, right? Negative 2 and 2 are not in the domain of the function. So why don't I take the time right now to specify the domain. The domain of f of x is equal to x such that x doesn't equal to 2 and x doesn't equal to negative 2. All right. So if x lies between negative infinity and negative 2, choose any number and plug it into this vector, the first vector, and the output would be a negative sign. Now, x squared plus 2x plus 4. Well, that's always positive. Okay, so that is always positive. You can, and I'll leave it to you to discover why. To discover why it's always positive, you can always graph the function, and you'll notice that x squared plus 2x plus 4 never falls below the x-axis. It's pointing up, and no matter what value of x you plug in, positive output. Now, this factor x, okay, so x minus 2 is always below the x-axis when x is less than negative 2, and the same goes for this factor as well. So, between negative infinity and negative 2, f of x will be the product of a positive number and a negative number divided by a product of two negative numbers, and so that is always a negative number. So that means on this interval, f of x falls below the x-axis. Now for negative 2 to 2, if we choose a value of x from negative 2 to 2, what happens? Well, this factor remains negative, this factor goes positive, and this factor remains negative. So from negative 2 to 2, the function is above the x-axis. Okay, and so from 2 onwards, okay, what happens? Well, this factor is positive, this factor is positive, this factor is positive, and so for x greater than 2, the function lies above the x-axis. So please don't forget your table of farms, otherwise you'll have a lot of difficulty in sketching the graph of the function. So we can go back to our graph now. Where was it? It was on this page, the next page. Okay. All right, so we have so we had y equals negative 2. I'm sorry, not y, x equals negative 2 is the vertical asymptote, and then we had y equals x as the slant asymptote, and then we had a hole at 2, 3, and we had a y-intercept at 0, 2. Okay, so we have that. So this is the structure so far. Now, we know from the table of signs, from negative 2 to 2, the graph is above the x-axis. So let's demonstrate that. So let's say y is equal to x cubed. I need to put that in parentheses, right? X cubed minus 8 divided by x squared minus 4, and x is greater than or equal to negative 2. Okay, and so that's shown by this purple branch. See the purple branch right here? Okay, so let's investigate this. The purple branch is clearly above the x-axis. It's asymptotic with the vertical asymptote, and it's asymptotic with the slant asymptote. You can see that structure. Now, there's one little mistake that's shown on this graphing calculator, and that is, you see the solid fill of the hole? Let me take it out and see if there's a little bit of, okay, so if I take it out, it vanishes entirely. So there's a mistake here. This graphing calculator isn't as concise as I was hoping it would be, and here's why. It's showing a solid fill here, but in fact the graph really doesn't exist here. So what you're going to have to do is when you have holes in your graph, you're going to have to go back and correct the mistakes of these graphing calculators, and you're going to have to annotate it as an open circle. The open circle means that there's no content of the function here. Okay, so make sure you adjust for the error in this calculator. All right, and so okay, so now we need to draw the next portion of the graph for x less than -2. Now we know for x less than -2 from based on our table of signs, the graph is below the x-axis. So where do you draw it? Do you draw your content here or here? Well, if we draw our content here in this portion, adhering to the asymptotes, you'll see that it would rise above the x-axis, and that can't happen. So the only two places where you can draw your graph would be in this zone right here. So we can fill in let the graphing calculator complete that for us. Okay, so the next piece. Can I copy and paste? Will it let me? Yeah, I think it'll let me. So we'll go Control V. Nope, Control Z. So no copy and paste in this. Doesn't have the video drivers. Okay, so x cubed minus 8 divided by x squared minus 4, and x will be less than or equal to -2. So that'll be the remaining piece. What happened? Sorry, I don't understand this. I guess I have to put the numerator in parentheses. Okay, do you understand that? Let me try it again. Y is equal to x cubed minus 8 divided by x squared minus 4, and we want x less than or equal to -2. Right, and that'll be shown in black. And there it is. You'll see the black content shown right here. Okay, fair enough. And now we, of course, have some local minimums and local maximums. Okay, so let's talk about that. All right, so before we proceed with calculating the coordinates of the local mins and local maximums, it appears see right there, I'm putting dots where those points are. We need to calculate those coordinates. Let's go back and review briefly about the increasing and decreasing components of a function. So clearly, if we consider this point right here as being a local maximum, for this branch, we see that to the left of the local maximum, the function is increasing. And why is that? Because you see as x increases in this direction, then y correspondingly increases in this direction. Okay? And then at the local maximum, again, it's a point of transition, so we pick up from the local max to the right of this particular local max. As x increases, then y decreases, right? It follows the negative vertical asymptote. Okay, so you can see it's decreasing. So we're transitioning from increasing to decreasing, and the point of transition is a local maximum. Now conversely, look at the purple branch of the curve. As x increases, y is correspondingly decreasing. Okay? And at the point of the local minimum, the transition from a decreasing notion to an increasing notion, that is, as x increases, y correspondingly increases as well. So we have an increasing portion of this branch. So when we see this behavior, then we need to identify the coordinates of the local max and the local minimum. I'll do one for you. How about we calculate the coordinates of this local max, and then I'll leave it to you as an exercise to calculate the coordinates of the local min, which will be done in a very similar fashion. So let me erase all the markups. Okay, and bear in mind that this point is a hold. So as from last class, to calculate the coordinates of this local max, we have to build a function table for now. And so we'll have to wait until chapter 4 when we can do it more efficiently. So our function table, x f of x. So we can kind of estimate that it's going to be somewhere around x equals -4. Right. So we'll go on either side of -4. And look for a pattern of increasing, decreasing, increasing, transition, decreasing, that is. So say -4.3, -4.2, -4.1, -4, -3.9, -3.8, and so on. So maybe this range of values, somewhere in this range of x values, we can identify the local maximum. All right, so let's see. Let's point our. So we have at -4, the output is -6. So we could write -6 here. How about if we move along? This thing do floating point? It doesn't appear to be doing floating point. Oops. You may have to resort to using a calculator. Yeah, the granularity of the pixels isn't that great. Okay, so let's see. Let me pull up a calculator on my desktop. I'm not sure if you can see this. So I'm going to calculate the output at -4.3. So 4.3, let's see. So I'm plugging in -4.3. -8 equals that divided by squared. And so when I do that, the output is -6.039. And again, always check, make sure that my calculations are right. So -6.039. I'm wondering if this thing, instead of using the calculator, how about I just do this? I bet you I can use this graphing calculator to calculate it. So if I go, so let's see what the output is at negative 4.2. So can I, yeah, let's see, negative 4.2 squared, cubed, right? Let's break. Cubed minus 8 divided by minus 4.2 squared minus 4. So what is that? Minus 4.2. That'll be the red dot. And that the coordinates are negative 6.018, right? So we can write, oh, there it is. Okay, so let me fill in the table. Negative 6.018. See how that works? All right, so let's do the next one, which is negative 4.1. So we'll go negative 4.1, comma, negative 4.1 squared minus 8 divided by negative 4.1 squared, squared that is, minus 4. And that would be the blue dot. So let's see if it shows the blue dot today. Negative 4.1. 4.1 squared. Oh, I need to put parentheses around here. I believe I need to put those in parentheses. Like that. So I think I have to put it in coordinate form. Well, let me try it again. Let me delete this. Try it again. Let's try it again. Let me erase this dot here. It's getting in the way. Okay, so let's try. So we want the function output at negative 4.1. So negative 4.1, negative 4.1, negative 4.1 squared minus 8 divided by minus 4.1. Oh, that should be a cube, sorry. Squared there, minus 4. Does that look right? That looks right. Okay, so that would be the green dot. So let's see if it plotted. Yeah, so there it is. So what are the coordinates of the green dot? 6.005, minus 6.005. Okay. So that would be minus 6.005. Now, if the function output at negative 3.9 is less than minus 6, then we're done. Okay, so or we're pretty close to the minimum or the maximal value. All right, so let's do the next one, negative 3.9. So we'll have negative 3.9, negative 3.9 cubed minus 8 divided by negative 3.9 squared minus 4. That would be the purple dot. So let's see what the graph has to say about the purple dot. So the coordinates of the purple dot, so that would be minus 6.005. All right, so look, you see how the function is decreasing up to negative 4? Then it starts decreasing once we get to the right of negative 4. So clearly, negative 4, negative 6 would be the coordinates of the local maximum for this graph. All right, so that's how you would analyze the local maximum. And again, I'll leave it to you to calculate the coordinates of the local minimum. Done the same way. Okay, so while on the topic of calculating coordinates of local minimums and local maximums, oftentimes we don't have to resort to using the function table, and that would be the case of quadratic functions. So let's talk about how to find the coordinates of a vertex of a quadratic function without using a function table. So let's see, let me erase all of this. And you can use this for future reference. And go on to the next slide. So just a brief discussion with quadratics. So let me insert a quadratic formula. So let me helpful one here. Get used to this. And of course, I need to insert the formula itself. Let's see, all right. All right, so here's the quadratic equation, ax squared plus bx plus c, and we know that we have the solutions, the two roots are found using the quadratic formula. So a review from algebra. So let me give you an example of how we can find coordinates of vertices of parabolas, which we know to be either a minimum or a maximal point. So y is equal to negative 2x minus 5x plus 3. So we're going to graph this function in light of the notes that we have so far. So to do so, with parabolas, we know that when we consider the leading coefficient of a parabola, in this case the leading coefficient is -2, if, I'll write this down, for parabolas, if the leading coefficient is greater than 0, then the parabola points up and the vertex is a local minimum. If the leading coefficient is less than 0, then the parabola points down and the vertex is a local maximum. And it's also a global maximum, so we'll discuss that in chapter 3. So in this case, for this example, the vertex will be a local maximum. And we can use the quadratic formula to find the x-intercepts, or we can factor this parabola. And so let's try factoring it. Let's do both, use both techniques as a means of review. So if we were to factor this, y is equal to what? -2x times x. So this would be what? -1 here. Is that right? -2x minus 3x. Yeah. 3 minus 2x. Okay, so there's the factorization. And then when we set each of the factors equal to 0, we'll have a means of computing the x-intercepts. And so that would equal to what? 3/2, -3/2, 0. That would be 1, and then the other one would be at 1, 0. All right, and then the y-intercept is just found by setting x equal to 0. And so when x is equal to 0, the output would be 3. So now let's calculate the vertex. So the way we calculate the vertex is we find the vertex by completing the square. All right, so let's do that. Now, I'll give you the procedure. So, step 1, factor the leading coefficient from the first 2 terms. All right, so let's do that. So, go back to my pen tool. So y, when we factor the leading coefficient, which is -2 from the first 2 terms, we'll have y is equal to -2 times x plus 5/2 x plus 3. All right, so that's step 1. Step 2, take 1/2 of the coefficient on x, and x being in parentheses. All right. So we take this 5/2, and we take 1/2 of it, and so 1/2 of 5/2 is 5/4. Like that. So do that. Okay, so let's go back. Step 3, square the term found in step 2. Okay, so doing that, when we square 5/4, we get what? 25/16. Like that. Step 4, add the number found in step 3 to the terms in parentheses. All right, so when we do that, we'll take the 25/16 and we'll put it here. Okay, all right, so we've done that. Now, when we add 25/16 to the term in parentheses, we notice that we have changed the equation so that now this new equation is no longer the original parabola. So that brings up step 5. Add a constant to the new equation to offset the addition in step 4 so that we get the original equation. All right, so here's what I mean by that. So when I added 25/16 to the content in parentheses, what I've really done is I've subtracted -2 times 25/16. I've actually added a -50/16 because when you distribute the -2, you're actually adding -50/16 to the parabola. See this right here? So we have -50/16. So since we've added -50/16, we have to, by step 5, subtract a -50/16. That should be a minus. So you see that I'm subtracting a -50/16. And now we have the original function back, okay? And also note that the 3 terms, the trinomial in parentheses is a perfect square. And so what we're going, so for step 6, what we'll do, step 6, convert the perfect square trinomial in parentheses to a binomial square. Right? So if we were to do that, here's what we'll get. We'll have y is equal to -2 times x plus 5/4 quantity squared and go ahead and simplify this constant term right here. So that would be 48/16 plus 50/16, which is 98/16. So we're left with 98/16. So we'll do 2 things at once here. And so there's the equation. I guess you call this the standard form. Perhaps, I can't remember the exact term, the standard form expression for the parabola. Okay, now, when we have the standard form of a parabola is typically written as this. X minus. When you transform the equation of a parabola into a format that looks like this, okay, then the vertex of the parabola is extracted from H and K like this. Okay, so you see how this form, this generalized form of a standard representation, matches this specific example. And so from here, we can deduce our vertex So the vertex is at negative 5/4 because in this case h is negative 5/4, right? Because we have plus is the same as saying minus 5/4, okay? And we have to have a subtraction. See the subtraction right here? We have to convert this addition to a subtraction, and when we convert the addition to a subtraction, we have to negate this number. All right, so the abscissa of the vertex is negative 5/4, and the ordinate, I'll go ahead and reduce this, would be 49/8. All right, so this is how we computed the local or absolute maximum of this parabola, and we're ready to sketch it. Okay, so we can just bring in our calculator. All right, so next page, we'll go ahead and sketch the graph of this. All right, so we had y is equal to negative 2x squared minus 5x plus 3. And it's sketched in red here. So here's our vertex. Yeah, so it's negative what? Where do we say the coordinates of our vertex? Negative. Let's check. I'll go back and check. Negative 5/4 and 49/8, which is 6.125 and negative 1. Yeah, so that was right. Yeah, so we're good. So it's going to reload. I know how to stop it from reloading now. I need to pin it. Okay, so y is equal to negative 2x squared minus 5x plus 3. Okay, so here's our graph. There's our vertex. Here's one x-intercept right there, negative 3, 0. And the other one was at 1/2. Right? And notice that it's pointing down. So there's a validation of our development work. And as you can see, since this is a local max, you can see to the left of the local max, the graph is increasing, right? The function is increasing to the left, and it's decreasing to the right of the local max. So everything's consistent so far. Okay. I think I can pin this. Yeah, so when I come back to this page, it won't jump around so much. Okay. All right, next slide. All right, so now continuing on with our algebraic review, I want to talk about functional transformations. Transformations of functions. All right, so what do we mean by this? So when we translate functions, we can translate, we have what? Vertical translation. We have horizontal translation. Then we have a combination of 1 and 2. And then we have other kinds, right? We have reflection. We have vertical stretching, shrinking, and then we have horizontal stretching. shrink, if I can spell right. So these are the kinds of transformations that we'll be dealing with. As a matter of fact, the first project that you'll be doing will be an application of a horizontal translation of a rational function. So at this point, I would suggest that you go ahead and start working on your first project. It is posted on the class website. So now let's go and talk about these concepts. Let me go back to the graph we had here, and I'll just do it mainly by example. So let's see here. What kind of interesting things can we do here to make this topic nice? All right, so let's graph. Let me set the window properties. It'll let me. Window settings, so let's set it into radians. I'm going to motivate this using a trig function, a trigonometric function. All right. So let's start off with the graph y is equal to cosine x. That's not cosine x. Oh, the y-axis is, darn, let me fix the window settings. I want the output to be this way. Why is that not right? Y is equal to cosine x. Do I need to zoom in, zoom out? Try it again. That is not right for oh, let's delete this. Try it again. Window settings. We'll make the x-axis in terms of pi, make the y-axis in terms of numbers, and what else? We use Cartesian. Cartesian, okay. Strange. Is that better now? Yeah, okay. So our first graph will be y is equal to cosine x. And it's drawing a straight line, which it should not be doing. Cosine x. This calculator seems to be having difficulty. Well, cosine x is not a straight line. Plus 3. Not sure why it's, let me check, hang on. Let me check my notes. Let's see. It was working last time, wasn't it? Oh, maybe that's it, f of x. Maybe I need to write it in terms of f of x. Let's see, f of x is equal to cosine x. Wow, that's really strange. Why did it all of a sudden stop? Hang on. Doesn't like something. All right, there we go. Okay, so maybe I have to keep it in rectangular coordinates. Okay. All right, so idiosyncrasy of the calculator. So here we've shown the graph y equals cosine x, and let me see if I can revert back to the x-axis being shown in polar. Yeah. All right, so that's the order of operations. And let me change the zoom box so that y ranges, say, between -2 and 2. All right, so you're more accustomed to this, I would believe. Let's make it 5 because we're going to be doing some stuff here. So we'll go -5. Will it not let me? Okay, well, leave it at that then. Okay, so here we have our typical cosine function. Now, what would happen if we were to vertically stretch this graph? I'm sorry, vertically, not stretch, but how about we'll start off with something less complicated. Let's say we have a vertical shift. So a vertical shift would, of course, occur when we add a number to the output. So the output right now in the original curve is cosine x, but if we add a number to the output, this will result in a vertical shift. So for instance, if a equals 1, you see that the orange curve gets shifted up by 1. Okay. Now if a is, say, I need to zoom out, right? Let's zoom out a bit. So as I increase a, you see the blue curve as it shifts upward in the upward direction. So for positive values of a, the curve will shift up. All right. So now if I go back down to 0, the blue curve will match up with the red curve. Now if a is, of course, negative, what happens? Then the curve starts going below the x-axis, going in the negative direction. You see how the blue curve is shifting downward? So here's your vertical shift action. All right. So we'll leave that right there. And so now how about a horizontal shift? So a horizontal shift, and this is something that students get caught up a lot on, is if we were to do something like this. It's where we take the input and we modify the input. Okay, we're not modifying the output. What happens here is the graph will shift either left or right in the x direction. So the purple curve would be an example of a horizontal shift. So you see the purple, how it's a little bit off from the original red curve. So if I were to shift the graph to the right, okay, a right shift would mean that I would have to use negative values for b. Okay, so notice that as I take my slider and I move it to the left, the graph of the purple curve moves to the right. So when b is negative, that is a right shift. Okay. Now when I add numbers, when I increase b, okay, in other words, as b increases as I move my slider to the right, notice that the purple curve is moving to the left. Okay. So this is a left shift. As you increase b, the curve shifts to the left. So positive values of b map to a negative translation, a negative translation in the x direction. Negative values of b map to a translation in to the right on the x-axis. All right, so as I increase b, or as b is positive, the graph shifts to the left. If I decrease b, or b goes negative, the graph shifts to the right. Okay, you see how that works? So go online and practice this if you need convincing. So we've done vertical shifts and horizontal shifts. All right. Then the other kind of shifts that we can deal with would be reflections. So basically a reflection is simply taking the negative of the graph, and that's shown in black. All right. So let me get rid of the purple graph. Now you see the black curve? The black curve is basically the outputs of the original cosine function multiplied by -1. And you see how it flips the curve about the x-axis? So this would be reflection. Okay. Now, let's talk about, oh, okay, so this would be, I'm sorry, this would be reflection in the x direction. No, I'm sorry, reflection about the x-axis. So how about if we were to take the inputs now, and we multiply the inputs by -1. What is the effect here? So the effect is, well, because the cosine function is an even function, we know that cosine of x is simply equal to the cosine of -x. So there's no effect on negating the inputs. So I'll show you an example where negating the inputs does reflect the graph about the y-axis. Well, in fact, this is happening, that we are reflecting the graph about the y-axis, but and I'll give you a better example other than the cosine function. While here, though, let's talk about stretching and shrinking. So we'll talk about next vertical stretching. So vertical stretch occurs when we take the outputs and we multiply it by a scaling factor. Right? So right now, when c is equal to 1, what do we have? We basically have the original function. Let me take this graph off. There's too much clutter with this one. Let's see which one is in the way. We can get rid of this one, and we're talking about okay. So all right. So what happens if we increase the value of c? Well, we would expect the graph to be vertically stretched. In other words, it's going to get bigger. So let's do that. So see, if c gets bigger, it becomes stretched vertically. Now the red curve is the original cosine function. Now when we decrease c, watch what happens when we decrease c. The curve shrinks. Right? You see the blue curve? It becomes compressed in the vertical direction. Right? Until we get to c equals -1. And when c is equal to -1, we basically, it turns into a reflection. Okay, so at c equals -1, it's a reflection. So between -1 and 1, okay, between -1 and 1, if I can get it, the curve is basically vertically compressed, or this is a vertical shrink. Now, if c, let me write this down. So insofar as vertical shrinking goes, all right, if we have, let's see, not negative. If we have at least for this graph, if we have this condition on c, the graph is shrunk vertically. Now, if we have this condition on c, the graph is shrunk vertically, and since c is less than 0, it's reflected about the x-axis. So watch again what happens when we have C between -1 and 0. Okay, you see there? See the blue curve? It reflected about the x-axis and it shrunk. Now, when C is less than -1, okay, well, you will also have, not only will you have a reflection about the x-axis, but you'll have a vertical stretch again. So look at the values of C. C is -4 in this case. We had a reflection and a stretch. So a number of things. Now, if C is greater than 1, all we have is merely a vertical stretch. No reflection here, okay? Again, C less than -1, we have a vertical stretch followed by a reflection. C greater than 1, only a vertical stretch, no reflection. Okay, so you have to be careful about these multiplying coefficients. All right, so that's the concept of vertical. All right, now how about the concept of horizontal stretching and shrinking? So let's see what happens here. This ought to be interesting. So let's go y is equal to cosine d times x. And we'll add a slider for d. So let me get rid of this one. And let's look at the graph. So when d is equal to 1, there's our fundamental graph. Okay. Now what happens if we increase d? What do you think is going to happen if we increase d? Well, the graph will shrink horizontally. So let's do that. We anticipate that the graph will shrink horizontally. So, and lo and behold, it does. See, as we increase d, we get more compression. We're compressing in the x direction. You see the compression there? Let me add an offset, so it'll be. So let's stop this. Okay. Stop. What are you doing? I don't want that. Get rid of this. Okay. And let's get rid of this. Let's get rid of this. Okay. Straighten it up. Okay. So compare the purple graph with the red graph. Okay. So as I decrease d, the graph becomes more stretched out. So this would be a horizontal stretching. This going in this direction, horizontal compression. Going in this direction, horizontal stretching. Okay. And again, when d becomes less than 1, say if d is between 0 and 1, we have a considerable amount of horizontal stretching. And so when d goes to 0, well, the cosine of 0 is basically 1, right? And so the output becomes 4 in this case. So if d is equal to 0, the output is 4. Now, owing to the even nature of the cosine function, as d ranges from 0 to -1, okay, we're going to have the stretching, the horizontal stretching. But as soon as d goes greater than -1, then we go back to our horizontal compression, as you can see here. So there's your horizontal compression. Okay, so try to understand these transformations of the graph. All right, so let's do the same thing with another graph. Let's get rid of this graph, and let's get rid of this graph, get rid of this graph, and let's say, how about we consider y is equal to the square root x to the 1/2. All right. So, and let me change my window settings now. So I'll use, okay, so let me zoom out. Let's always zoom in. And let me change the y bounding. So let's say y ranges from -10. Let me get rid of this. Okay, so let's say It'll equalize the x-axis. Okay. So y is equal to x to the 1/2 square root function. So it's shown in red here. Okay, so everybody sees the square root function. Now, let's apply the same operations. So a vertical shift would be something that looks like this. So this would shift the red graph down 2 units, as shown in blue. See that? A horizontal shift, well, you can only shift this graph to the right. So that means we would have to subtract something from the x argument. So a horizontal shift 2 units to the right would be something like this, the green curve. So you see the green curve? Its x-intercept now changes to 2, 0. So this would be our horizontal shift to the right. Remember, we're subtracting a number from the argument x, and that shifts the graph 2 units to the right. Okay. Now, next graph, say, how about a reflection? So y is equal to negative x to the 1/2. Okay, and so that would reflect the red curve right here about the x-axis. So the purple curve you see is reflected. Okay, and then we can do a vertical stretch. So how about y is equal to 2 times x to the 1/2. So this would be a vertical stretch. So you see the orange curve is a vertical stretch of the red curve. Okay? And then we can do a reflection about the y-axis by negating the argument. So how about y is equal to negative x to the 1/2. Okay? Now in this case, x has to be less than 0. Okay, note that x has to be less than 0. So let me write that in here. Note for reflection about the y-axis, the domain has to be such that x is less than or equal to 0. Okay? Otherwise, you can't. If x were positive, you'll be taking the square root of a negative number. You'd have a complex result, and we don't do complex numbers in this class. All right. Now, we can do try one crazy thing, I guess. We can do a vertical shrink or a vertical, I'm sorry, not a vertical shrink, but a horizontal shrink. So how about y is equal to, say, 3x to the 1/2. And so this would be the red curve. Is there anything of interest here? Well, so when we did this, we basically divided. Well, let's compare. So we have we see what happens when we multiply the inputs by 3. Look at the resulting output. The resulting output is multiplied by the square root of 3. So it's basically what it amounted to is that we divided the input by 3. So when we did a horizontal, well, actually it resulted in a vertical stretch. So this resulted in a vertical stretch for this particular function. So multiplying the argument by 3 pretty much resulted in a vertical stretch for the graph. Okay. Let me see if there's anything else about function transformations. All right. Yeah, there is one more, and that would involve taking the absolute value of a function. So one other thing that I want to deal with respect to function transformations. Let me pull up a graph here. Bear with me, I'm hunting for another picture. Okay, so let's see, let me delete these graphs, and we'll talk about taking the absolute value of a function, something we'll do a lot in this class. All right, so let's consider the graph y is equal to x squared minus 1, which is your fundamental parabola shifted 1 unit down. Now, what would happen if we took the absolute value of this function? Well, when we take the absolute value of a number, then this piece below the x-axis has to be reflected above the x-axis, right? Because in absolute value, nothing can be less than 0. So let's see. Y is equal to absolute value of x squared minus 1. And note, you see the blue part that was below the x-axis in the original function, it's now reflected above the x-axis. So you have this crazy looking, quirky looking graph. Okay, so what would happen if we were to vertically stretch this graph? So it would look something like this. All right, so the purple curve is a vertical stretch. And look at the dynamic of what's going on here. See the vertex that happened here? All right, the vertex was originally at 1, but since we multiplied it by 3 in a vertical stretch, then the vertex got moved up to 3. And look at the branches. The branches kind of folded in toward closer to the y-axis. So that's kind of interesting, what's going on there. What would happen if we were to change the 3 and say made it a smaller number? Well, we would anticipate that the ensuing branches would be to the left of the green branches, right? So let's try that as our next graph. So y is equal to 0.5 times the absolute value of x squared minus 1. And as we anticipate, the branches flared out. They moved away from the green branches. And look at the vertex. The vertex shrunk down to 1/2. So there's a very demonstrative example of a vertical shrink or a vertical stretch, if you will. I guess this would be a vertical stretch. I always get stretching and shrinking mixed up, so I'll just call it a transformation. Okay, so how about a horizontal stretch? Now that things really get interesting with a horizontal stretch for this graph. So y is equal to, say, absolute value of, now this time we'll multiply x by 3 square minus 1. Aha! So look what happened here, the black curve. So let me delete the verticals. And so the vertex stayed the same, but this would be a horizontal shrink. Compare the black curve and the green curve. Okay, we shrunk it horizontally. We compressed this curve. What we're doing with the horizontal shrink, in the horizontal shrink, we are dividing the x's by 3. Okay, and that's what's resulting in the horizontal shrink. Okay, so now conversely, if we want to do a horizontal stretch, okay, we would have to choose a number, say between 0 and 1 as the factor on x. So y is equal to, say, x divided by 3 quantity squared. minus 1. And it's rather dramatic now, right? So this would be a horizontal stretch. Notice that the x-intercepts move to -3, okay, and to 3. Whereas in the original graph, they were at -1 and 1. Okay, so this would be an example of a horizontal stretch. Okay. Anything else? All right, so that takes care of other functional transformations and depicting them in familiar ways. All right, oh, and I guess we could do some exponential action here. I would be remiss if I didn't do anything. So how about y is equal to 5 to the x, like this. So there's your quintessential exponential function. Now, compare that with, say, y is equal to 1/5 to the x. What do you think that's going to do? Well, it's going to basically reflect the graph about the y-axis. So this is a reflection. How about y is equal to log, say, 5 of x? Can we put in the 5? I'm not sure how we would do a log function. I know it's functions. Here we go. Functions, calculus, yeah. Let's delete this. I'm not sure how to functions, calc. It doesn't allow me to drag the functions. Double clicking doesn't work. Dragging doesn't work. Okay. Log. Let's see. Log is 3 of x. All right. Yeah. So I guess that's how you would represent that. So here we have log base 3 of x. Okay, so to add some perspective. All right. Okay. Okay, just some interesting ideas. So now the next topic I want to talk about would be functional composition. So next slide. So let's talk about composition of functions. And your first project will involve this. All right, so we say if we have two functions, f of x and g of x. So we write the composition of two functions using this notation. F composed, we use this circle operator. F composed with g of x. And that is equal to, well, you simply replace x with g of x. Okay? That's all function composition is about for the most part. So for instance, if I give you, say, f of x is equal to 1 over 1 plus x. And I give you g of x is equal to 1 over 1 minus x. All right, so the question is, what is f composed with g of x. All right, and so one thing you can do is you can write it like this. We take f of x, and then I draw this long vertical bar. This is called the evaluation bar. And what it means is, if I write this like this, the evaluation bar means that I take all the occurrences of x in the definition of f of x, and I replace it with g of x. So this would equal to 1 divided by g of x. See how I replaced x with g of x? And then the next thing you do, of course, is you replace g of x in your expression with the definition of g of x, which is 1 over 1 minus x. And then you can simplify. So that would be 1 minus x divided by minus x. Okay. Let's see, 2 minus x, excuse me. 1 minus 6 over 2 minus 6 would be the composition of the two functions. Now, if I had, say if I interjected a third function, say if I have h of x is equal to 1 over x. Well, we can do a triple composition. That would be possible. So we could do f composed with g composed with h of x. And so that would just simply be f composed with g of x evaluated at x equals to h of x. Okay, and so that would equal to 1 minus x over 2 minus x, if my math is correct, evaluated at x equals to h of x. And that's just equal to 1 minus h of x divided by 2 minus h of x. Right? And so we just wire in the definition for h of x. That would be 1 minus 1 over x divided by 2 minus 1 over x. And so that's equal to x minus 1 over 2x minus 1. So there's a triple composition. All right. So with composition, you have to be a little bit careful with the domains of a composition. So let's talk about the domain of a composition of functions. So I'm using the uppercase D to denote the domain of a function. So the domain of a composition is what? Well, there are two rules. If x is not, this means not, in the domain of G, then x is not in the domain of the composition. X is not in the domain of the composition. All right, so that's one thing. The other rule is, concomitant with this, is if g of x is not in the domain of f, it's not an element of the domain of f, then X is not an element of the domain of the composition. All right, so two rules to know when analyzing the domains of compositions of functions. Let me see if I have an example. I thought I had one. Maybe not. I may have one in my algebra notes. Let me check. Bear with me. Let me go through my take a quick look at my algebra stuff. Yeah, I see one here. All right, so let's do a couple of examples from my algebra notes. Let me go to another page. So let me copy something. Trying to find an interesting problem. Yeah, here we go. Let me, yeah, I found one from my algebra notes that was useful for calculus as well. I'll paste it. Let's see, Control V. Let's see, print screen. Control V. All right, so select this. Yeah, I'm pulling up a note on composition that might be useful. Let me paste it in here. Okay, so let's look at this example from the algebra text. It has utility for calculus. So let's let f of x be this rational function right here, and we let g of x here. So we want to find the domain of the composition as well as finding the composition. All right, so find the domains of f and g. Okay, so for f of x to be a real number, x can't be 0 right here. See, obviously x can't be 0. So the domain of g, written using interval notation, is any number that's 0. So I'll assume that you're familiar with this alternative form of interval notation. And for f, since any real number except 2 can be an input to f, the domain of f is here. So here we have, as everybody knows, the domains of these rational functions. So now we want to compute the domain of the composition. So the domain of the composition, okay, is a set of real numbers x such that x is in the domain of g and g of x is in the domain of f. Okay, so x is in the domain of g and g of x must be in the domain of f. That's another way of looking at the domains of compositions. So all values of x but 0 are in the domain of g, and all values of g of x but 2. Okay, so if g of x is equal to 2, that can't be in the domain of the function. So we have to exclude 0 from the domain and the values of x where g of x is equal to 2. All right, so where does g of x equal to 2? Well, g of x is 1 over x, so 1 over x is equal to 2, so x is equal to 1/2. So the domain of the composition, right here, here's the key point. The domain of the composition is a set of all numbers, real numbers except 0 and 1/2. All right, and so written in interval notation, all the numbers, real numbers except 0 and 1/2 are written like this. All right, and then this technical note goes on to show you the composition of the two functions, and we've done an example of that already. Okay, so this is a kind of an advanced example of analyzing domains of compositions of functions. So what's next? So why do we have compositions of functions? Well, it kind of leads to the next topic where we talk about functions and their inverses. So let me go to the next slide. And I think I can pull up an algebraic note as well on this. There's some good notes. So let's talk about inverse functions. So before we go to inverse functions, a function has an inverse. Before we need to go on to that aspect of it, we need to talk about the concept of one-to-one functions. So let me give you a definition of one-to-one functions. Let me pull up a reference note here. All right, so one-to-one functions. A function f from a set x to a set y is called one-to-one if and only if different numbers in the domain of f have different outputs. Okay, so you can't, so for instance, like y equals x squared is not a one-to-one function. Right, because we have different inputs yield the same output. Like if x is -1, the output is 1. If x is 1, the output is 1. So we have basically a many inputs to one output. So not one-to-one. Also, a notation I use for one-to-one would be this. Okay, this symbology means one-to-one function. So look at this example right here, a generalized example, the red function. Different x values right here, see? x1 and x2 yield the same output, so this red curve is not one-to-one. Here's an example of a one-to-one. In figure B, see different inputs yield different outputs right here on the y-axis. At least on this interval, it's a one-to-one function. All right. So how do we determine if a function is one-to-one? Well, we have the horizontal line test, but there's another easier, more efficient way. Let me show you how you, an example of how you can ascertain whether a function is one-to-one. Let me pull up a technical note. Let's see. If I can find it. Yeah, so let me give an example of determining whether a function is one-to-one. So here will be an example. Say f of x is equal to 1 divided by x minus 3 minus 7. We want to show it's one-to-one. So look at, here's an alternative definition. A function is one-to-one when if f of a is equal to f of b, then is a equals to b. All right, so here's a definition. This is what you would use to determine if a function is one-to-one. So for instance, so we take our function f of x and we plug a in for x. So we have 1 over a minus 3 minus 7. Now if it's one-to-one, then that must equal to 1 over b minus 3 minus 7. All right? And so after simplifying this particular expression right here, okay, we need to solve a in terms of b. So compute f of a, set it equal to f of b, and then solve for a in terms of b. And so in solving for a in terms of b, follow the algebraic steps, trace the algebraic steps. If a equals to b, when you solve for a in terms of b, then the function is 1 to 1. So this would be a classic example of determining whether a function is 1 to 1. Now, why do we want to know if functions are 1 to 1? Well, it turns out that 1 to 1 functions and I'll use this symbol for 1 to 1, functions have inverses. All right? So, for instance, let me give you an example. Let's find the inverse. Let's see how to find the inverse of a function. Let me give you a rule here. And then I'll follow it up with an example. So here's the strategy for finding the inverse of a function given f of x. So step 1, we replace f of x with y, interchange x and y, solve for y, and then replace y with this notation f negative 1x. Now, this is not an exponent. All right, so be careful in the context. This negative 1 is not an exponent. That means the inverse of a function. So I'm going to use this strategy for finding the inverse of, say, f of x. So f of x is equal to 1 minus x divided by 1 plus x, right? And we want to find, that's a plus, we want to find f inverse of x. So we'll use the strategy. Step 1, replace f of x with y. So y is equal to 1 minus x divided by 1 plus x, right? And then we solve for y. So to solve for y, I'll cross multiply. So I'll have y times 1 plus x is equal to 1 minus x, right? And so I have y plus xy is equal to 1 minus x. And let's see, I'm trying to solve for, let's see, what is it? Okay, solve for y, right? Let's see, let me check. Yeah. So then I can factor, let's see, yeah, so I'll get the x's on one side, and so I have xy plus x is equal to, I'll move this x over, and then that's equal to 1 minus y. So then I have x plus see, I'm trying to solve for y in terms of x, right? So I have x plus 1, or did I not do that right? Let's see. Xy plus x is equal to 1 minus y. Oh, I'm sorry. I need to get the x's. I need to get the x's on one side. Sorry, redundant step there. We have xy plus y is equal to, sorry, I shouldn't have done that. Go back. I need to solve for y in terms of x. So we have y times x plus 1 is equal to 1 minus x. And then if I divide both sides of the equation by x plus 1, I'll have y is equal to 1 minus x over 1 plus x. And that's equal to f inverse of x. Okay, so interestingly enough, the function is and its inverse are the same functions. Let me give you, perhaps I should give you a better example. So let me show you one which isn't so obvious here. Next page. Pull up an example. All right, so it got truncated here, but I'll write it. I'll fill it in. We want to find the inverse of 3. Oops, sorry. Got smeared there. I'll write it out again. We want to find the inverse of 3x divided by 2 plus 2. All right, so calculate the inverse of this. So step 1, here's the function right here. F of x is equal to 3 halves x plus 2. Replace f of x with y. Then we interchange the variables x and y. So x now becomes 3 halves y plus 2, and then we solve for y. So algebraically solve for y. Here are the algebraic steps. I won't go over them in detail. And so once we solve for y, then we replace y with f inverse of x. Now, the technical note here is, how do we know that this is in fact the inverse? Well, it turns out this little rule right here. A function composed with its inverse of x should equal to x. All right? So let's go back and check our previous example and verify that this rather peculiar example of the function and its inverse are the same. If we compose the two, we should get x out. So in other words, if we compose f composed with its inverse like this, we want to check, does that equal to x? So let's do that. So we'll go through the algebraic manipulation. So f is this. F is equal to 1 minus x over 1 plus x, and we want to replace x with its inverse. Okay, and so that's equal to 1 minus f inverse of x divided by 1 plus f inverse of x. All right, and then we plug in the definition of f inverse of x, so that would be 1 minus x divided by 1 plus x divided by 1 plus 1 minus x over 1 plus x, and we need to simplify this expression, and so that would equal to, so we'll multiply upstairs and downstairs by 1 plus x, and in doing so we get 1 minus x divided by 1 plus x plus 1 minus x, and we simplify, so that's equal to 2x divided by 2, which is equal to x. So yes, so we validated the inverse. Okay, and if you need to see another example, I'm not sure, does this note? Yeah, this note does it as well. Well, actually it doesn't. Oh, it does do it. Okay, so let me copy that. I'll paste that, how they validated it for this particular example, so you can have another choice here. Let's see. I won't go through it, but I'll just post it here for your reference. Okay, so let me paste that here. Here's the check. And if you're not comfortable with this or a little bit rusty in the techniques, go through these details. Okay. Oh, also note that how they checked. Not only did they check this composition, but they also checked the composition of F inverse with f of x. You actually, technically speaking, you should do it both ways. So going back to our check for this example, all right, I checked it using F composed with F inverse. You see that right there? To complete the check, technically speaking, I also should do this calculation as well. I should compose F inverse with F to be a rigorous check, because there may be a quirky example lying out there where this doesn't happen. It'll happen in this direction, but it won't happen in this direction. And if it doesn't happen in this direction, then the function has no inverse. I can't think readily of an example of that, but the procedure for checking the inverse should involve both compositions, evaluating both compositions and getting the result x. Okay? All right. So function composition. This will be very important when we talk about taking derivatives of functions. We'll need to know that we'll need to be very proficient in this skill. So let me check my notes, seeing how far we have to go. Okay, so all right, so let's do a review of exponents and logarithms. Another topic that calculus students often come unprepared for. So just as a reminder, laws of exponents. Let me see if I have a technical note here. Functions, properties. See if there's something I can paste in here. Well, I'll go ahead and write it. So remember, if we have a base, A, where A is greater than 0 and not 1, okay, and the exponent is a function of two variables, then by the laws of exponents, we can distribute the base thusly. All right, so we can, oh, sorry, even I'm wrong. That would be written as a to the x Yeah, I was right. I'm sorry. I had it right. A to the y. We can distribute it the base with respect to exponential addition. So here we have exponential addition, and we can take the base a and distribute it with respect to that and have this expression. With respect to exponential multiplication, if we have a to the x, okay, if we have this expression raised to another exponent y, then all we do is we merely multiply the exponents. Okay, so these expressions are equivalent. What else? Laws of exponents. Now if we have something like, well, no, I guess that's sufficient. Okay, let's talk about logarithms. A technical note on logarithms. Okay, so symbolically written, the logarithm of a function, the log of x, log base a of x, okay, that y equal to this. So this is just an expression. And this is true if and only if, what? A to the power of y is equal to x. So exponentiation is the undoing of logarithms, okay? Logarithms are the undoing of exponentiation. And so it's really a trick. You just take the base, the logarithmic base, and you make it an exponential base. And then the output of a log function becomes the exponent, all right? And then you leave the argument alone. So this is how you transform from exponential form to logarithmic form. And then, so we have a number of tricks we can do with logarithms. If a is equal to, say, e, the irrational number e, which is approximately equal to 2.71828. Okay, so log e is often written as natural log. All right, and another rubric for logarithmic functions, if the base is 10, log base 10 of x, well, we just drop the base. That's the only time we drop the base. Log base 10 is x. So when you see a log function in this class written without a base, then it's assumed the base is 10. Okay, so I'm going to distinguish between log base x and natural log of x this way. Here base is 10, here base is e. Oftentimes, especially in engineering literature, these two functions are used interchangeably. So the literature can get quite confusing, so you have to be careful the context in which you read about logarithmic functions. All right, so logarithmic properties. So the log of a product of functions or quantities. So if I write something like this, okay, that translates into a logarithmic expansion of a sum. Okay, and then the logarithm of a quotient of quantities, well, that translates into a subtraction, a logarithmic expansion of the subtraction of the quantities. Okay, and then if we have logarithmic exponentiation, say x raised to the power of number n, okay, well that just, the exponent of the argument of the log function becomes a coefficient in the logarithmic expansion. So that would be, right, and so you'll use these ideas to do logarithmic expansions and contractions. So there are other interesting formulas. So for instance, if I have a, and in my exponent I have the log base a of x, okay? Well, that is just equal to x for all x greater than 0. Okay, so I've introduced a new math symbol. This upside down a symbol, translation, means for all. Okay. All right. What else? All right. Now, another interesting thing about, suppose I ask you to calculate something like this, log base 3 of 4. Okay. You can't typically type this in on your TI series calculator. So what you have to do is you have to convert this into something that your calculator can handle. And so the rule is this would simply be the natural log of 4, which you can do on your calculator, divided by the natural log of the base. So for instance, if I have log base b of x, or b is some quirky number, maybe some irrational positive number, okay? Well, this is just simply equal to the natural log of x divided by the natural log of b. So this formula will come in very handy at times. All right, so for instance, let's see if I have a couple of examples of applications of logarithmic functions. So let's do some logarithmic and exponential equations. Okay, let me paste a few in here. I'm not going to spend too much time on this review, but I'll refer you to some examples that might be useful as we go along. So here are a couple of examples. I won't trace the details, I'll just paste it into the lecture notes. So here's another property of logarithms. If log base b of x is equal to log base b of y, then x equals y. All right, so for instance, look at this. If we want to solve for x in this logarithmic equation right here. So the logarithmic bases are the same. So 3x plus 2 is equal to 2x minus 3, so x is equal to negative 5. Here's another example where the bases are the same. Now consider this one, log x plus log times x plus 3. So here we have a logarithmic expansion on the left-hand side. So remember, a logarithmic expansion, you can convert it to a logarithmic contraction by multiplying. You see this x and the x plus 3 right here in the logarithmic expansion? Well, if we were to contract it into a log, it would be log x times x minus 3. And why do we want to do that? Well, we have a right-hand side, which is a constant, okay? Right here, the sum of two logs is the log of a product. And the reason why is because we want to reduce the expression where we have just one log on the left-hand side, okay? Because we can take the anti-log of both sides. The reason why we want to contract the logarithmic expansion is so that we have one log on the left side, and that allows us to use the definition of logarithms, in other words, to take the anti-log. Since the base is not presented here, the base is assumed to be 10. And what we're doing is, in this example, is we're using this concept right here. We're transforming the logarithmic expression into an exponential expression. Okay? And since y is a constant, okay, y is 1, we now have a constant on the right-hand side, and we have an expression in x on the left-hand side. So to solve logarithmic equations like this, we have to transform the equation into one without logs, okay? And once we recast the expression into one without logs, then invariably what shows up is a polynomial expression, okay? And then we can solve polynomial expressions using our standard techniques. So this is what this is all about. Just transform the expression, the equation, into one without logs. It's the same with absolute value, which I'll be showing you next. We transform the expressions into one without absolute values. Okay. And then they go on and solve in this example. So solving the algebraic expression, we have x equals negative 2 and 5. There's a potential for extraneous solutions, so always check. Negative 2 isn't, so like in this case, negative 2 is not a solution because we can't plug in negative 2 into a log, because remember the domain of the log function, if you recollect the graph. of any log function, that would be x has to be greater than 0. And since -2 came out as a solution to this equation, if we plug in -2 here, we'll have log of -2, and that just doesn't happen. All right? So we reject -2 as a solution. So go through this example when you have a chance. Let me erase the scribbles so that you'll have a clean view of it. Okay, please trace the logic. Very important here, especially in Chapter 3. When we get to Chapter 3, we're going to be dealing with this a lot. All right. So other things we can deal with would be absolute value. Let me see if I have some good and useful notes on absolute value. Okay, so what I want you to do for absolute value is, I'm not going to consume too much class time, but I want you to take a look at this link. Let's see. Refer to okay, here's a link. It's a rather comprehensive link of solving equations with absolute value. And it's replete with examples. So for instance, if I have the equation absolute value of x is equal to a number, then the solution would be x is equal to k, or x is equal to -k would be the solution. All right. If I have something like all right, so consider this example. Solve x plus 2, absolute value is equal to 7. All right, so you can see the solution there. Just go step through a couple of examples. Solve quadratic, absolute value of a quadratic is equal to 7. So here's the solution here. So see if you can duplicate the results shown here. And here would be a graphical solution to this particular absolute value inequality, or equality rather. So here's the absolute value of the square root function, of the absolute value of the quadratic, shown here, and then the four solutions plotted here. Okay, how about solving equations with two absolute values? Let's see if I can, probably need a new page, right? Okay. See if I can get this. Let's see. So here's an example of how to solve equations with two absolute values. All right, so take a look at this note. So it looks like a little bit of it got truncated. Let me copy it again. Still truncated. Let's see. All right, that's better. It's kind of, sort of. So look at this, solving absolute value, an inequality with two absolute values. And let's see here. All right, so now solving inequalities, right, with absolute value. So let me give you an example. Let's see here, let's zoom out. So when we have absolute value less than the number, by example here, so absolute value, solution to absolute value with inequalities kind of proceeds the same way when we solve logarithmic equations. We have to take the original equation, like this, for instance, the original equation, and we have to transform it into an equation or an inequality without absolute value. See how we transformed it? So when we have absolute value less than a number, we wedge the quantity that we're taking the absolute value of between the negative of the number and the positive of the number. And the resulting inequality doesn't have absolute value anymore. And then we algebraically solve, and we see that x is wedged between these two numbers. So trace the details of this. And then likewise, when we have absolute value bigger than a number, say something like, give you an example. Okay. So control M. All right, so here's an example solving absolute values greater than a number. And again, we transform the problem into one that doesn't involve absolute value. And so with greater than, we make the argument of the absolute value less than the negative of 5 and the argument of the absolute value greater than 5. And we solve algebraically and we get this result. Now, in chapter 2, we're going to be reversing this technique of solving absolute value being greater than or less than a quantity, and we're going to be working backwards. We're going to be taking inequalities like this, and we're going to be converting them to absolute value. So let's see how that would work. So I'm glad I mentioned this. So a couple of examples where we're given inequalities and we want to convert inequalities to absolute value. So let's see how that works out. So we'll be doing this a lot in Chapter 2. So suppose I want to convert this inequality into one of absolute value. So the idea is we need to get the endpoints right here to be the same value in magnitude. So in this case, we want the magnitudes to be 3. And so we adjust by adding and subtracting quantities to the inequality to make the magnitudes of the left and right endpoints the same. And so converting this expression, this inequality, into one with absolute value would involve manipulating the endpoints. And for something like this, x less than 19 or x greater than 24, whenever you have a situation like this, an OR situation, then the result, again, you would hunt for the endpoints, okay? And so you note that the endpoints are 5 units apart, and so you have them, and so this would be your targeted constant that you would want to set the absolute value greater than or equal to. And so with 2.5, you would have to add and subtract 21.5. Okay, so here's an example of converting inequalities to absolute value. Okay, let's see, and a couple of other examples solving. Yeah, one more example of solving inequalities with 2 absolute values. Okay, there are all kinds of games we can play with these. So we want to solve this one, and now again, here we're using the alternate definition of the absolute value. Recall that the absolute value of a number is also equal to the absolute value of x squared. And so we replace the absolute values with the square root notation and squaring both sides and then algebraically solve. So take a look at this example. You have some more interesting ideas. Okay, yeah, here's one. Suppose we wanted to graph a function with 2 absolute values. Again, we would resort to reformulating the function into one without absolute value. So consider this. Let me copy it for you. So here we're translating so let me go to another slide. So what if we wanted to sketch the graph of this function with absolute value? So we have f of x is equal to the absolute value of x minus 2 minus the absolute value of x plus 1. So we want to graph this function. All right, so what we would do is we would use a definition of absolute value, and we would replace x minus 2 with its expression not involving absolute value, as well as x plus 1, and then we do the subtraction. So for x less than -1, okay, for x less than -1, the absolute value of x minus 2, right here, is equal to this, if x is less than -1. So we replace it as an expression without absolute value. And then, of course, the absolute value of x plus 1 is equal to negative x minus 1 when x is less than 1. And why don't we go ahead and make this an addition. I'm going to go ahead and fix that. I'm going to make this an addition, okay? And so we have, this is the function when x is less than -1. When x is between -1 and 2, so in other words, when x is greater than or when x is less than 2, but greater than -1, we replace absolute value of x minus 2 with its expression, and then we replace absolute value of x plus 1 with its expression when x is greater than -1, which is x plus 1. So here we have x plus 1. So this is the expression right here. And then when x is greater than 2, we replace absolute value of x minus 2 with that right there, and then we replace absolute value of x plus 1 with x plus 1. So f of x then is a piecewise defined function. I'll go ahead and simplify this. This would be negative 2x plus 1 for x less than -1, and it would be 3 for -1 less than x less than 2, and then it would be 2x minus 1 for x greater than 2. Right, and so we can graph that. Let's go back to our graphing tool. Did I pinpoint it? Oh, we'll just go ahead and insert another one. Insert. Let me put the cursor here. Extend the page. Insert. It's not. Well, I guess I have to do it on another page. All right. Okay. And so we'll pull up our graphing calculator. And so what was our function? We had a piecewise defined function, right? So for x less than -1, it was negative 2x plus 1. So negative y is equal to negative 2x plus 1 for x less than or equal to -1. And so you see the branch right here. Here's the red branch. Okay. And then for x between -1 and 2, we had x is equal to 3. So y is equal to 3 for -1 less than or equal to x less than or equal to 2. Okay, and you see it as drawn as the blue component. And then for x greater than 2, we had y is equal to 2x minus 1. So y is equal to 2x minus 1 for x greater than or equal to 2. Okay, and that's shown in the green curve. All right. So what's interesting about this graph is these corner points, and that's what they're called. So whenever you're graphing absolute value functions, you can anticipate having these corner points, and lo and behold, they happen to occur at -1 and at 2. Okay, so we'll be doing a number of these graphical structures with absolute values. All right, so what next? Okay, so let's talk about inverse functions now. This will be the last topic of lesson 1. All right, so let me erase this graph. And let's go ahead and graph y is equal to cosine x again. Go back to our favorite function. Or how about not cosine, let me use sine. I think sine will be easier at the outset. So let's make it sine x. All right. So here's y equals sine x. Now, what is it? In the context of one-to-one functions, I ask you, is the sine function a one-to-one function? No, it's not, because look, at -2 pi the output is 0. At 0 the output is 0, and at 2 pi the output is 0. So we have many inputs mapping to a single output. So what's interesting is that a property of a one-to-one function. So this, well, the sine, okay, so one-to-one functions have inverses. All right. So do we have a conflict here? Sine function is not one-to-one. Yet, if you look on your calculator, most calculators, they have an inverse sine function on them. So what's going on here? Did the calculator guys screw up and put an inverse sine function? When clearly the sine function doesn't have an inverse because the sine function is not one-to-one. Well, it turns out that they did not screw up. The issue is that when we talk about the inverse sine function, we're not talking about taking the inverse of the entire function. Okay, we're only talking about taking the inverse of a portion of the sine function, namely the principal part of the sine function. So if I were to go back and graph y is equal to sine x, and I restrict my x between -pi halves and pi halves. So watch what happens. Now look at the orange curve. Okay. See the orange curve? Let's zoom in. That orange curve, okay, is one-to-one. Okay, it's clearly one-to-one. So when we take the inverse of a sine function, we're only taking the inverse of this orange function. We've actually defined a new function. We restricted the domain of the sine function. If we restrict the domain of the sine function to -pi halves to pi halves, we can take its inverse. Okay, so the black curve is the inverse function. All right, so what is it about the inverse? Let's compare the orange and the black curves. No, this isn't Halloween. All right, so we note that the domain of the sine function. Now, when I restrict the domain of the sine function to negative pi halves to pi halves, we've got what's called the principal sine function. And so principal sine function is typically written using an uppercase. Okay, so this means principal sine. When I use uppercase letters, that means that for sine, I'm restricting its domain from negative pi halves to pi halves. So there won't be any confusion with the normal sine function, which domain is the entire x-axis. So the domain is what? The absolute value of x is less than or equal to pi halves. Right? And when we take the inverse, okay, I'm sorry, let's talk about the range of the principal sine function. So the range of the principal sine function is the absolute value of y is less than or equal to 1. Okay, now, how about the inverse? The domain of the inverse sine function, okay, and I'm using uppercase, well, that is simply, what we do is we simply flip the domain in the range. Okay, that is the absolute value of x is less than or equal to 1. So when we take the inverse of a function, we're effectively doing this. We're effectively flipping the domain in the range. Okay? So likewise, the range of the sine inverse function, okay, is equal to, well, the absolute value of y is less than or equal to pi halves. Okay, I flipped the domain in the range on the inverse calculation. So see right here, I flipped the two, and let's do some point calculation. So what are the coordinates of? Let me go back to my graph. Hello graph. Let me get back to my Internet Explorer. You zoom in. That's a bit slow. All right, so this is a technical problem, but yeah, so for instance, on the orange curve we have pi halves 1. And so on the black curve, we would expect 1 pi halves. So the coordinates of this point right here would be 1 pi halves. Whereas the coordinates of this point are pi halves 1. Okay? So that's a peculiar property of inverse functions. So what does that really mean? So let me erase all the scribbles and give you another structure to be conscientious of. Let me erase all of this. Take this away so you can see better. And let's let's zoom in some more. Now, it turns out that a function and its inverse, no matter what the functions are symmetric with respect to the line y equals x. All right? So the red line is y equals x. So what that means is a function and its inverse. If I were to plot a point on the function, so this is y equals principal sine x, then its symmetric counterpart would be this, because of the notion that we flip the domain in the range. And so functions and their inverses are symmetric with respect to the line y equals x. So I thought I'd sneak that note in there for you. All right, so that's inverse sine. So we can talk about inverse cosine, if this thing will let me. All right, so let's get rid of this function, get rid of this function. We can leave y equals x there. And let's say y is equal to cosine x. Okay, so that's shown in blue. Zoom out a bit, get the feel for it. And again, as you can see from the blue graph, it is not one-to-one. So we need the principal part of the cosine function. And so if we take, now the way we ascertain the principal part is we look for an interval on the x-axis where the cosine function goes through its full range of values, say from -1 to 1. And so on this interval right here that I'm highlighting, we'll choose this interval as the interval for the principal cosine function. So let me erase that and we'll sketch the principal cosine. So let's restrict our interval from 0 to pi. Get rid of this. Oops. So we'll say 0 less than or equal to x less than or equal to pi. And there's this is the graph of our principal cosine. And so now to graph the inverse, because, well, let me make sure you see it. So clearly this blue arc, the principal cosine, is 1-to-1. Now to graph, and so this 1-to-1 component then graph will now have an inverse, and so that would be y is equal to cosine inverse of x. Okay, and that's shown in green right there. Note that there's symmetry about the line y equals x. Okay, there's symmetry about the line y equals x. So if I pick, let's see how you make it stick. So here's -1 pi. So we would expect pi -1 to be on the graph as well. And so there it is. Pi -1 is on the graph. Okay, so there's symmetry with respect to the x-axis. All right, and then we can do the same thing for the tangent function. So let's get rid of this. We'll talk about the arctan function. Okay, so y is equal to tangent x. Okay, so what would be an interval where the tan function spans its entire range? And that would appear to be, say, between what? -pi12 and pi12. Okay, so let's restrict the domain of the tan function to -pi/2, 2, less than or equal to x, less than or equal to pi/2. And when we restrict that, then this would be, the purple graph is actually the principal tan, and we have to use uppercase, right? But it's not shown on the calculator. So this is y is equal to principal tan. And now we can consider the inverse tan function. And so, as you would surmise, we would flip the domain in the range. So next graph would be inverse tan. So y is equal to tan inverse of x. Okay, that will be shown in yellow. And you can tell that the purple and yellow curves are symmetric about the x-axis. Okay, so inverse trig functions, inverse trigonometric functions. All right, I think this concludes our discussion of our algebraic and trigonometric reviews. So this would conclude my Lecture 1 topics. So what's next? All right, so here are the deliverables. You have a web assign that needs to be completed. You have a project 1 that needs to be completed. Note the due dates on the class website. And also we need to have a test on Chapter 1, which will cover these lecture notes. So here's what I have an expectation of. I have an expectation that you understand completely these video lectures and the notes therein. We'll have a recitation. What I'll do is we'll work in class a number of representative problems that will be on the test, the Chapter 1 test. And so that will be how we'll progress for this class. So come to next class. I'll send the class an email as to when we will meet for a recitation, the times at which we'll meet for a recitation. And also use the recitation opportunity to bring any questions or problems that you wish to have worked. Okay, and then we'll have our Chapter 1 test. So that is it for Lecture 1. So let's see here. So I will end the discussion now. And I'll try to save the lecture notes this way. So recording about to stop. Recording stop.